Hello everyone. I wanted to continue our discussion about scaling up computation in Ethereum. We saw in the previous classes we talked about Yoda, and this time I wanted to talk about another one of our papers, which is called Tuxedo. So Tuxedo is going to be presented in ACM Sigmetrics. 2022. Okay. Now, the flavor of Tuxedo is quite different from Yoda. So, with Yoda, we were doing off-chain computation. So, what I meant by off-chain is that miners don't do the computation. For these computationally intensive transactions. Of course, there are other transactions that the miners do execute. Of course, there's some advantages to this, that each CIT can have quite a large amount of computation. But the drawback was that CITs can't interact with each other. CITs of, let's say, different smart contracts, which we call CICs, do not interact. I should say cannot interact. Okay. So this is a little bit different from Ethereum, where you have transactions getting executed one after the other, and pretty much each smart contract or each transaction can, in theory, call functions from any other smart contract. Okay. Okay. So this was a shortcoming, but of course each CIT could have, in theory, any amount of computation. So this is of course in theory, but in practice there might be some limitation. Right? You may not want, in theory, to wait forever for a particular transaction to execute, right? So the system might put some bound on computation that a CIT can execute. Okay. So Tuxedo is quite different. In here we make some minor changes to the Ethereum protocol, and all miners do the computations of CITs. So this is on chain. So all miners do, let's say, the CIT computation. And in addition, like Ethereum, any CIT can invoke functions of any smart contract. However, there can't be there's no such thing as a free lunch, they say, right? So there is some bound on how large these CITs can be. Okay. So the flavor is quite different. Yoda we saw became quite complicated because we had to offload the computation to these execution sets and so on, and we had this miracle algorithm and rice algorithm and so on. Here we won't need any of that because every miner is going to do the computation himself. So there is no need to run anything like miracle and so on, right? Or rice algorithm and so on. But what is the trick that we use? So there must be something because at least as far as we saw with Ethereum, we couldn't do much computation, right? Because of the verifier's dilemma. So let's revisit Ethereum a little bit before we go into Tuxedo. So in Ethereum, suppose this is at some particular miner. Suppose he receives a particular block. So what does this block contain? It contains many things, but we will focus on two things. So one is the transactions in the block. And it contains a hash of some state. So this is the hash of the state of the EVM after executing TI. Okay. So what is this? Well, let's say that these are the state variables. Each of these, few of them could belong to a particular smart contract, another set to another smart contract, and so on. But we have some sort of Merkle structure here in Ethereum, and this root is what you put in the block. So it is, let's just say it's a Merkle root. Okay, so the exact details you can find in something called the yellow paper on Ethereum. Okay. So let's just, for the timing, assume that we have a Merkle tree over here for all of these state variables which are at the, let's say, the leaves of the Merkle tree. Okay. And this is put in the block. Okay, so this set of transactions TI are executed all, and the state variables updated, and this new Merkle root is computed and it's put in the block as SI. Okay. So what is this particular miner supposed to do when he receives this block? It takes some time to validate. And what does validation involve? First of all, it has to ensure, first of all, it would have to execute the transactions. Okay. And basically the execution involves updating the state variable. So all the variables in the various smart contracts. And what he would have to do, he would have to compare the Merkle root with SI stored in the block. Right. So this is at a high level what the miner has to do. Of course, there are other things too. There are other rules in Ethereum. Just like there are various things. For example, does the proof of work, is the proof of work valid, and so on, right? Those things we are skipping right now. We are just focusing on the transaction executed. So this is what happens in the validation, right? So it takes some amount of time to do this validation. After this, the miner creates his own block. So I'm just going to call this let's say he puts his own set of transactions ti plus 1. I'm going to call it ti plus 1 dash, and he has to put an appropriate value for the state, representing the state over here. Okay. So how is this block created? So he has to choose ti plus 1 dash from his own transaction pool. Okay. So of course the transactions that were included in ti are removed from the transaction pool, and so ti plus 1 dash is chosen, right? And now he would have to execute these transactions. And put the new root in the block. Okay, so I'm just going to call this dash. Okay, so when I put a dash, it means I'm referring to this particular miner. This is the potential block which he has created. This block may not get into the blockchain if he's unsuccessful in doing the proof of work, right? But here, this is the block we are assuming which has come from the network from somebody else, which has a valid proof of work. Okay. So after the miner has created this block, he is going to do proof of work. So this is proof of work on his own block which he has created. Okay. So this we have looked at in an earlier class in a lot of detail, and we said that The validation and creation time has to be small compared to the proof of work time. Otherwise, you have something like called the verifier's dilemma. Right? So that we've studied in detail in an earlier class. So validation plus creation time are kept low. Okay. And in practice, Ethereum keeps this to hardly 1% of interarrival time between blocks. So this is from our own measurements. This is just 1% of the interarrival time between blocks. So this seems a pity that we have a CPU, but it's only running for 1% of the time. Okay, so if we look at the hardware, what really is happening? So let's look at this particular miner, what hardware he is using at what time. So let's look at one typical interarrival time between two blocks. Let's say this is where BI arrives. So there is a very short time for validation. And this is for creation of BI plus 1 dash. And then we have a POW on BI plus 1 dash, and then let's say over here BI plus 1 arrives. Okay, let's say somebody else was successful in mining the block and this block arrived here. Okay, and then again the whole procedure repeats. So this is what happens, and which part of the hardware is running. And since proof of work is some standard algorithm, right, and you want to do it really fast. I mean, if it's something like hashing, the more hashes you do, the higher the chances of your winning. So this is done in application specific integrated circuits, ASICs. So ASIC is on over here, right, during this time, and here this is not done in the ASIC, this is done on a CPU, right? This is just transaction executed. So I'll just say that the CPU is on over here. And what about here? Well, the CPU is pretty much off over here. So what we do here, of course, depends. I mean, I think in an earlier class we had discussed, you could create an empty block, for example, while you're creating BI plus 1, you could create, let's say, an empty block. And you could run POW on it, right? That might be possible, right? But our focus here is on the CPU. Let's focus more on the CPU, and let's just assume for the time being that ASIC is off over here. You could sort of hedge your bets and assume that BI, the BI which you received is valid, and even while you're doing the validation, you could try to create an empty block on it, right? But those sort of optimizations with some probability of doing the right thing, you can have some optimization, but let's for the time being just assume that in this time the ASIC is off. So to summarize, Ethereum is essentially shrinking the validation and creation time to about 1% of the total interarrival time between blocks, just so that most of the time can be spent on proof of work, and the miners can avoid the verifier's dilemma problem. So as a result, the CPU is effectively working only for 1% of the time, and for 99% of the interarrival time between blocks, the CPU is not working at all. Okay? So what we would want to do in Tuxedo is to make the CPU work 100% of the time. Okay. And how are we going to do this? Because it seems impossible to do. After all, if we increase this time, we know that we're going to hit the verifier's dilemma. Okay, so obviously we'll have to change the protocol a little bit, but hopefully not too much. And of course, when we change the protocol, we may face other types of problems which we hadn't anticipated, and we'd have to deal with those. Okay, so we want to make the CPU work for 100% of the interarrival time between blocks. So how are we going to do this? So let's think, what does a block creation involve? Okay, so we talked about block creation here. So what we are doing here is that we we choose a set of transactions from the transaction pool and order them, and then we execute them over here. Okay. So we do both of these in the creation. So what if we do only one of them? Suppose while doing creation, I just order a set of transactions from my transaction pool and put it in the block. Okay. And what if I delay this execution to some time in the future? Okay. So that's an idea. And what about validation? Okay. So validation, here we execute this TI, right? And we have to do all of this. So can we make validation much simpler? Okay, and can we somehow delay the execution of these transactions sometime into the future? Okay, so this is going to be what we are going to try to do in Tuxedo. Okay, so normally block creation involves ordering transactions and also executing them and updating the state. Okay, so what we are going to try to do this is we're going to try to separate these two out. Okay. So let's think of a block. Suppose we have block BI, and this has transactions and the state. The details of Tuxedo, let's see why we actually put the state in the block. Okay, so we said that miners have to execute these transactions and verify that the state is the same. Okay, so we'll have to keep this at the back of our minds because we are going to play around a little bit with this process when we actually discuss Tuxedo. So why do we put SI? So why not just order transactions and put them in? Why bother to put the state in over here? Okay. So we have to understand that in Bitcoin, for example, there was no such thing as a hash of the state being put in the block, right? But we do it in Ethereum, and the reason is that the state variables are not on the blockchain itself. In Bitcoin, pretty much the entire state is on the blockchain because of the UTXO model. But here you essentially have code in the transactions. So the state variables are stored, the values and so on are stored in the EVM, the Ethereum virtual machine, right? And the blockchain itself just has the code and it says which functions are called and so on, right? So what is the purpose of putting SI over here? So first of all, it forces all miners to execute these and update the EVM. And it makes them do this immediately. Okay. So this is important because otherwise maybe a lazy miner would not bother to do it. Suppose this was not there, and somebody was, for example, creating a block, he could just put some transactions in and just send it off. Why bother to execute them? And that could lead to all sorts of issues. Maybe the transactions are invalid, or maybe they are junk, whatever. So this forces miners to actually execute the transactions, right? They need to put the right state in here. Okay. So otherwise, lazy miners may not execute the transactions. Okay, and essentially all that we would have in this whole Ethereum would be just ordering of transactions, but really what we want is that we need to update the EVM state, right? And by putting SI here, we force everybody to update the state, right? And even somebody receiving the block, of course, while creating it you have to do it, but while receiving the block too, you have to update the state and check whether the person creating the block has done it correctly or not, right? So this is important to have the whole Ethereum working. So any miner pretty much has an up-to-date EVM state in Ethereum. Okay. Also for light clients, so a light client may just have the blockchain, he may not have the EVM state. say suppose he has only the blockchain. Or maybe only the block headers, let's say. Now suppose somebody wants to prove to him that there is some particular data in the EVM state. Okay, now how would you do it? We said that you have the root, and let's say you have many state variables here. So what you can do is you can prove that the state is so and so, or a part of the state is so and so, by finding a Merkle proof and showing it to the light client. So the light client effectively knows at least the hash of the state. He has this root, and so anybody can prove to him some particular state that it wants, right? So this is another reason why we put the state or the hash of the state in the block. Okay? So what are we going to do in Tuxedo? So I've already given you a hint of what we end up doing. Okay, so in Ethereum, this is what the block BI looks like, right? And these transactions are executed, and the state is put appropriately in the block. Okay. Now in Tuxedo, what we are going to do is the following. So we have BI, and suppose there is a set of transactions we put in over here. I'm going to call them TI. Okay, and I'm going to look ahead at block BI plus Z. Okay, and in the paper we use zeta. I think it looks like that, right? But here I'll just use Z. Okay, it's easier for me at least to write it. Okay, and so this particular block has T transactions I plus Z, right? So this is the blockchain. Okay, and Z is some number, right? And what we choose in Tuxedo is Z has to be greater than or equal to 2. Okay. Okay. So what are we going to do here? Here we are going to do a little something tricky. So this Z is a parameter of Tuxedo. So based on various factors, we discussed some of them in the paper, we choose Z, okay? But you can choose Z is equal to 2, but you might in practice want to choose it a little bit longer, let's say 5, 6 or whatever. Okay. So now when I execute TI, I get state SI, and that I'm going to put over here. Okay. So it's a bit different. I don't execute transaction TI here and update the state. I am willing to delay the execution of TI and put the appropriate state over here. Okay. So this is what we call delayed execution. Okay. So the miners are not forced to immediately execute these, but they are forced to execute these particular transactions at least by Z blocks in the future. Okay. Okay, so why are they forced to do it? Well, because if you have to create block bi plus z, you better have the state after executing ti, right? Otherwise, you will not be able to create this block, right? And similarly, if you don't, if some miner, even if it doesn't succeed in doing POW for bi plus z, it might receive this particular block from somebody else, and if it doesn't have the state ready after execution of ti, then it's not going to be able to validate this. Okay, so miners have to execute ti before this block bi plus z to create or validate a block at that depth. Okay, so this is what we're doing, and so let's see how it all works out, and later after that we'll have to see what could possibly go wrong, and then we'll have to look at fixes for that, right? So how does this really help? Okay, so suppose we are at a miner and he gets bi. Okay. So what does bi look like? bi has some transactions ti and it has state I minus z. So what would have been in block I minus z in Ethereum, that particular hash of that state I am putting in this block. Okay. And what would be I plus 1 have? It would have t I plus 1 and state I minus z plus 1. Okay. And like I said here earlier, we need state si to be put in block bi plus z. Right. So suppose I order all these transactions right from the, let's say from the genesis, let's say this is the genesis block. And I come t minus 3, t minus 2, I minus 2, ti minus 1 and so on. So after executing all of these, I would end up with si minus 3. Right, after executing all of these, let's say up to here, I have si, right, and so on, right? So if all of these were executing right from the beginning up to ti, then the EVM would get updated to a state corresponding to si, and it's just that I am storing these states a little bit later in the blockchain, right? Okay, so I'm forcing the miners to execute these. It's not like I'm only doing ordering. I'm ordering them, of course, but I'm forcing them to execute at least before a certain block in the future, maybe a little bit into the future, right? So suppose this is what is coming at a particular miner. Let's say we are focusing on one particular miner. So what is this miner supposed to do? So here it has Si minus Z and Ti. What do I have to do to validate? Okay. So for the timing, we'll forget about whether the Ti has inappropriate syntax or anything like that. Okay. Let's just think about the state right now. Okay. So what we have to do is that we have to ensure that Si minus Z is correctly put in the block. Okay, and later on we'll have to think, what if Ti has something wrong, some state wrong and so on. Right? I beg your pardon, not state, what if it has some syntax wrong and so on. So let's for the timing assume that we already have Si minus Z before Bi arrives. Because there's a lot of time. Ti minus Z were the transactions in a block, Z blocks in the past, right? And in fact here we would have had Si minus 2Z. Right? Okay. So there was a lot of time. Let's say that Z is 5 blocks. We had 5 blocks to execute these transactions. Right? And suppose we had Si minus Z already with us, then this validation could have been done in a breeze. Okay, then validation is just a comparison. Okay, what do you have to compare? The locally stored value of Si minus Z, which let me call it Si minus Z dash, and Si minus Z in the block. So let's for the timing assume that we have this. Okay, and what do we do with Ti? Well, let's think about it. So you have the CPU, and the CPU has an execution queue. Okay, and maybe there is Ti minus 1, let's say, over here. Or let's make it Ti minus 2, Ti minus 1. So what we do is we dump this over here. Okay, and these are removed from the queue as soon as they are executed by the CPU. Okay. So once ti minus 2 is executed, we would have state si minus 2. Once we execute ti minus 1, we have si minus 1 and so on, right? So just in this particular example, I am assuming that there is a little bit of backlog. Transactions of the two previous blocks are still there in the queue. Okay, and I'm assuming that z is greater than 2, right? Because I'm assuming that I had this state over here. Okay, so this is done, and notice that the CPU is continuously executing these transactions. As long as the queue is non-empty, the CPU can keep executing the transactions, right? And we don't have to worry about immediately executing TI. So these transactions TI have to be executed before bi plus z. It's time for bi plus z to be either created or validated. Okay, so this is pretty good. Just by delaying this execution of the transactions, we were able to validate this state. Okay, so we are forgetting about other complications and we're leaving it for maybe the next class. So we just have to check this particular value, and we said we already had it ready with us because ti minus z was already executed. It's been removed from the queue, right? And we put ti at the end of the queue. Okay. So now what do we have to do? We have to create bi plus 1 dash. So what do we have to do here? We have to put some set of transactions ti plus 1 dash over here, and we have to put si minus z plus 1 over here. Okay. Now suppose z is equal to 4, just over here to be clear. Okay. So in this particular example, when this block arrived, I put this in the queue, and the miner already had processed ti minus 4 and ti minus 3. These were already removed from the queue. Okay. So he had si minus 4 and si minus 3. Okay, and so what is si minus z? In this particular example, of course, we could choose z to be something else, but let's say z is equal to 4. This is nothing but si minus 4, and si minus z plus 1 is nothing but si minus 3. Okay. So since ti minus 3 was already processed by the CPU, we already have this, and we could directly put this in the block. Okay. So creation of bi plus 1 dash was also pretty fast. So all I had to do is choose some transactions in my in my transaction pool, and since I already had si minus 3, I could put it directly in the block. So creation of bi plus 1 dash, okay, this is done locally by the miner. What does it have to do? It has to choose ti plus 1 dash from the transaction pool, and also put si minus z plus 1, which is si minus 3 here in the block. Okay, but this was already pre-computed. Okay, so creation was also very fast. So what did we end up doing here? We could create bi plus 1 dash without really executing ti plus 1 dash. And similarly, we could validate bi when it arrived without immediately executing this. Okay, so we already have some pre-computed states, and so validation and creation of blocks are just going to use those pre-computed states, and that's going to help us do the validation and creation really fast. Okay, so this is at a high level what we are doing in Tuxedo, and since we avoid execution of transactions, in validation or creation of bi, we essentially are going to avoid the verifier's dilemma. Okay, so the verifier's dilemma came into being because I was forced to verify the transactions immediately, and if the computation was very heavy in a particular block, then there was a temptation to actually skip the verification. Whereas here we are saying you don't have to verify the transactions immediately. You can do it a little bit later. And of course, as you probably already realized, that there are some problems which we'll have to deal with when we change the rules a little bit like this, right? But for the moment, let's keep that at the back of our mind. And so this is what Tuxedo is doing at a high level. You put the state appropriate to a block in a future block, z blocks into the future, right? And if you're able to finish the computation, all the backlogged computation till that particular block has to be created, then you're fine, you don't have to worry. But of course, if you miss that deadline, it could be a problem. And as we show in our paper through some modeling and so on, that if you choose z large enough, you don't have to worry about meeting the deadline. Okay, so what we've ended up doing is that in Tuxedo is that you can do POW pretty much all the time, and at the same time you can always in the background keep validating blocks using the CPU. Okay, so I'll just summarize that. So you have bi, so here you have si minus z and ti. So this arrives. So the validation is pretty fast. So we essentially check si minus z whether it's correct or not. And creation of the next block is also done in a breeze. Okay, so pretty much the entire time we can do proof of work. Okay. So we don't have to worry about the verifier's dilemma. Even if the computation here is somewhat heavy, we are not doing the computation immediately. We are leaving it for a little bit in the future. We are putting it in the queue, right? And the CPU is blazing away continuously, verifying, executing these transactions. So we are doing POW pretty much the whole time, and that's how we avoid the verifier's dilemma. So even if CITs are there in this, validation is trivial. So we will have to think how large can the CITs be. But anyway, what about the CPU computation? Previously we said that the CPU was on only during validation and creation and it was off here. But now these have been put into a queue. Okay, and the CPU is executing these. So as long as there is some backlog in the queue, the CPU can be active all the time. So as long as the queue is non-empty. Okay. So in theory, we've achieved what we wanted to do, that it's not that the CPU and the ASICs run one after the other, and while ASIC is running, CPU is off and so on. So we've sort of parallelized the process in such a way that the POW is essentially continuously running, because these validation and creation is trivial, happens very fast, and the CPU is continuously executing, and it may happen, and in fact we would desire it, that the queue would very often end up being zero, that the queue would not exceed beyond a certain size, and by design most of the time, let's say, the queue would end up being empty, right? So the CPU might be idle for some time in between, but we could design it in such a way that a large fraction of this interarrival time, so let's say that we get bi plus 1 over here, so a large fraction of this interarrival time could be, we could have the CPU being active, okay, by choosing these parameters appropriately, Z and so on, right, and the allowed gas limit in these blocks. Okay, so we look at finer details of Tuxedo in the next class.